Hey, it's Masaki from the Enza Competitive Programming Club, and I'm going to be discussing the practice contest problems. So A was 3 dice, and so what you need to know is that for each side of the die, the opposite side is going to add up to 7. So all you need to do is you have the numbers for dice A, B, and C, and then you need to add up 7 minus A, 7 minus B, 7 minus C. And you just need to add all 3 of these values. Another way, some people did it as 21 minus A minus B minus C. This will work as well. And I personally ended up doing it within a for loop. So if you think about the case where there might be 100 dice, 100 die, or maybe 1,000 die, or 10,000, it gets out of hand. So it's good to think about how can you convert this into a loop instead of doing minus A, minus B, minus C. It's also a good practice to try doing this as well for a larger test case. So for B, the question is called picture frame. You're given an image of height h pixels and width w pixels. So you get pretty much a 2D grid of characters, and each pixel is represented by a lowercase English letter. So a really good technique for this is to, after you input 2 integers, I would input 2 strings. So for each h, it's a good idea to have a vector. For example, if you're using C++, have a vector of strings or some kind of list of strings or something. That's going to make input a little bit easier, I think. And if you've never worked with 2D arrays and stuff like that, well, you work with 0, 0, and then you go row first and then column. So it's not like X and then Y, it's the opposite, kind of like Y and X, but usually you think of it as row and then column, and then 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and things like that. So this is row 1, and then row 1, column 0, 1, 2, or something like that. So this, yeah. So if you look at the sample output, problems like this, instead of reading through the problem statement and trying to figure out what you need to do, kind of breezing through this and then looking at the output can be really helpful. So here, what you want to do is, okay, so I want to box around this entire grid thing, but how many, I need to do 1 row of these sharp symbols, these pound signs first, and then this is W, this is the width of the grid, and then this is W plus 2. So maybe you can notice something like that. And then, okay, I want to print out the pound sign, and then the string, and then the pound sign, and stuff like that. So my personal implementation was like that. So input H and W, and then for W plus 2, output the pound symbol, W plus 2 times. There's a bunch of different ways to do this. You can create a string. There's different functions depending on your language of choice and stuff like that. But just output it W plus 2 times. And then for each time you input a new string, you can output the pound symbol, and then output the string, and then output the pound symbol. And then at the end, we also need 1 more row. So this is probably the easiest way of thinking about it. So C, we have on and off. So this one was a little bit tricky. Parts of the implementation, it was really easy to get wrong. So one hint is that it's 24 hours, and Takahashi has the same routine or schedule every single day. So it's not going to be more than 24 hours. So we have this 24-hour time window, and then we have some start, and then we have some end. S and then T. And then we have some X. So X can be here, X can be here, X can be here, or something. But it's not going to be on the integer, it's going to be 30 minutes past X o'clock or something. So X is some value plus 30. So if it's in between S and T, then you got it right, and then it's on, and if it's not, then it's not. but the tricky part is that the date may change while the light is on. So between 0 and 23 o'clock. So let's say you start at like 5 o'clock and then you end up staying awake until, so this is like 5 p.m. or something. So that would be 17 o'clock. You start at 17 o'clock and then you stay up until like 3 a.m. or something. Then that would be 3. And then if t is less than s, then we know it went past thing. So one easy way of doing it is t plus equals 24 or something. Just add 24 hours and that would work. And another way to do it would be to just have a bunch of if cases and stuff like that. But I think the easiest implementation is going to be to add t 24 hours to t if t is less than s. And then we want to check if x is in between s and t, but x might also be past like 0 o'clock. So if x is also past 0 o'clock, then we want to add x plus equal 24 as well. So if t is less than s and x is less than s, then we can add 24 to x. So that part, just need to kind of figure it out, maybe draw a picture. I think that's helpful. And then it's pretty easy. Is x in between s and t? So the implementation, I don't know if that was a good explanation, but if it's less than or equal to, the equal doesn't actually matter in this case. S is guaranteed not to equal t. So it's fine. And you can add 24. So think of it as the next day. And just so that you can work with x is greater than or equal to start and x is less than end. And we want x is strictly less than end because we want x 30 minutes past x o'clock. So if x and t are the same values, then we know that the light's not going to be on. It's going to, like, if you have the light on until 5 o'clock, then if you check at 5:30, so if x and t are the same, then at 5:30 it's not going to be on. So it has to be strictly less and then greater than or equal to. So that's the other part. And yeah, the other condition is if x is less than start, then add 24. If end is less than start, add 24. This doesn't have to be embedded within the loop, I think. I think it can be outside and it'll do the same thing as well. But this one, yeah, see, it can be pretty tricky and you need to think through all the cases. What if, one good idea might be, what if they're on the same date? So what if one is, what if they're both on the same day and it doesn't cross? And then think about what if it does cross and kind of work that out. And I think that would be helpful. D, UFO Invasion. You're given a string S of length 12. How many occurrences of zone does it contain? This contiguous substring. So zone was like a sponsor for one of the programming contests. But zone, how many of those are in this string of length 12? And 12 is very, very small, so you can do brute force on this. So if you look at here, A, B, C, D, and then you check and you can find something. You can find the string, you can find the string, you can find the string, and you're guaranteed that the string is this. So if it was like, if you can have a different string like A, like let's say it's like A, and then find A or something, then or find AA, then you might have overlap, but you also don't have to worry about overlap. You have to think about overlap, but these are 4 distinct characters, and there's no thing like that, nothing like that. So you just have to go through. The easiest way to do it, I think, with every language is going to be to think about each character as the start of the string and then check the substring from here to the length of zone. So the implementation is going to be from I, let's say this is the start position, I is the start position, and then s.size minus z.size. This is what you want to search for, and so we don't want to go out of bounds. So we only want to, the last thing we want to check is going to be this f character, for example, and you get a string of length 12. So that's going to be index 0, 1, 2, 3, 4, 5, 6, 7, 8, which 8 is 12 minus 4. So it's going to be s.size minus z.size. In the general case, we can do s.size minus z.size, but if you're just doing this problem in particular, then you're guaranteed to have it 12. So you can hard code it as 8, but it's also a good idea not to use hard coded characters if you can help it, and do what, and think about a broader case where you have to look for a different substring, or maybe you have to look for a different length or something like that. So this is going to be, it's useful to think about it in the more abstract sense, but if you have to, you can hard code 12, you can hard code 12 minus 4, stuff like that. But you can just do a for loop. Let's say this is the start of zone, and then check the next 4 characters. If they match up with the substring that you're looking for, then it's going to be a match, and otherwise no. So each index will be the start position, and then you just want to check the next 4 characters starting from that position, and check if it matches the substring. And this, you can also, if you want to look up a way to do it more optimally, there's other functions. So there's something called like Knuth-Morris-Pratt algorithm, a string matching algorithm. This is kind of complicated, but you can kind of Google it. I've never had to use it in programming contests, so it's definitely not really required, but it might be useful to know the existence of, just be aware that this stuff like this, so this would be an n squared algorithm, or n times m maybe. So this length of the substring times the length of the original string. So it would be kind of n times m. Might be one way to do it, but this is I think algorithmically n plus m, so it's significantly faster. So stuff like that be very useful to think about. And if you look at cases like this, you know that you don't have to check every single spot, so it'd be a good idea to kind of check this out. So E, beautiful matrix. Again, this is one of those problems that's really complicated if you read the text, but if you look at the example and kind of read it carefully, then you'll just see that, okay, we have a grid, we have a 5 by 5 grid, so we have dots, we have a 5 by 5 grid, and then you select one of them, and then how far does it take, how many steps does it take to move it here, or something like that. And it's just, well, if this, so again, this is going to be the I value, and this is going to be the J value. And this is going to be the row, and this is going to be the column. But we're trying to get to here, which is 2, 2. And then if you get, let's say this value is higher, then it would be J minus 2 and I minus 2 plus J minus 2, or something like that. And let's say it's smaller, then it's going to be, if this value is smaller, then it would be 2 minus J, or something like that. So in either case, you can do absolute value of 2 minus J or J minus 2. Either of those would work. And this is also called the Manhattan distance. So if you think about a city with a grid layout, kind of like Manhattan and New York, then you have all these roads, right? And you can't go diagonally through a block in Manhattan or something, you have to cross the street and then you have to cross the street again or something. And how many blocks away is this? Let's say you're trying to go to the store and you're at this location. How far away is it? This is called the Manhattan distance. And so you might go how many away in the I direction, how many away in the J direction. And this is going to be the same thing. We're guaranteed that the grid is 5 by 5, so that makes it a lot easier as well. So again, you just subtract 2 and then take the absolute value. Just work through a couple examples maybe, and yeah, the wording is not that great, but if you work with it, you'll kind of figure it out. So there's a lot of problems like this where it just sounds a lot more complicated than it actually is. So if you just read it through, and it won't be as hard. And this F is a really good example of that. This seems really difficult, but if you write out some examples, then it becomes a lot simpler. So first, you're given a string S. So let's just start with the example case, like AAB. We're given a string S of length n, and so this is length 3, I guess, n is equal to 3, and a number k. Let's denote reverse of S, the reverse string S, as S of n minus 1, dot, 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 S. So this is S, and then reverse of S would be BAA. And then you can replace string S with S plus reverse of S. So, or you can replace string S with reverse of S plus S. So this either becomes AAB plus BAA. So I guess you don't need the plus symbol. So it either becomes this string, or it becomes BAA AAB. And so there is option 1 and option 2. And how many different strings can you get as a result of performing exactly k operations on the original string S? And then this S, now the new S value becomes this. So if you can figure that out, it becomes a lot easier. First, you get a test, the number of test cases t, and then you get the next 2 lines will contain n and k, and then the string. So in this example, k is equal to 2. So this is the first operation, and then if you do one more operation, you either get maybe AAB, BAA, plus the reverse of that, which would be, well, if you look at it, this itself is reverse, so AABBAA. And what you'll see is that this is related to palindromes, right? And if you look at this example or something, ABA, CABA, then if it's a palindrome, then regardless of if you go with option 1 or option 2, you're going to end up with the same result. And another thing you can notice is that a palindrome, you're always going to end up with a palindrome after one step, because you're adding this and then you're adding the reverse of S. Right? Adding S and then the reverse of S, or reverse of S and then S. And then both of these are palindromes in every single case, because they match up, right? This is the reverse of the other string, so of course it's going to be a palindrome. And if you can realize that, then, well, the k steps don't really matter at that point. So you just need to check whether there's more than one k, and then if k is equal to 0, then you're only going to have the original string, so there's only one option. But otherwise, if it's already a palindrome, then you can't create any unique ones, and then otherwise you just check if it's a palindrome. So the easiest way, I think, in my opinion, to check if it's a palindrome is going to be to check the first n minus 2 characters, and then check if s of I, so let's say index 0 is not equal to, check if it's equal to n minus 1 minus I. So n is going to be 3, and then 2, and then 2 minus 0 is going to be index 2. So this is a way of matching the first and last string, and then second, and then second to last, third to last. This will always do that. Checking the index I with checking the index of n minus 1 minus I. So this is just a good little trick that you can use, and that's one way to do it. You can also do take the first and divide by 2 characters, and then take the last ones and then reverse the one string and then just compare it or something. There's other ways of doing it. It's going to be a little bit slower. It's going to be a little bit more difficult, I think, but that works as well. So yeah, this is going to be probably the easiest way to do it. You can, yeah. And you don't have to check about even or odd case as well if you do it in this way. And then after checking if the original string is a palindrome, you can check whether it's a palindrome and whether k is equal to 0. So that's all you need to do. In the end, it's only 1 or 2. The answer is only 1 or 2, which is it's kind of a trick question. It's completely a trick question, and it looks a lot harder than it actually is. You get really tricked by this k value, and they even have the 0 here, so another really kind of tricky element of it, but once you figure it out, yeah. So this is, again, an example of you don't have to actually do this operation. You can kind of logic your way through it and try to figure it out. And if you try to do 1,000 operations, then you're going to run out of time. So that's a big issue I think I saw some people had. Problem G. G was a pretty difficult problem. It was kind of a bonus problem. F and G were kind of bonus problems for this contest. But so you have n moves that you can learn, and each you have one to move 1 to n, and each move takes t minutes to practice to learn, and you have to learn moves a of I to a of k in order to learn another one. So let's just look at an example. So let's say you have move 1, move 2, and move 3, and then move 2 has the prerequisite of having to learn move 1, and then move 3 has the prerequisite of having to learn move 1. So basically, you the first number is how much time it takes to learn this specific move, and then you get how many prerequisites there are, and then so in this case there's one prerequisite, and that prerequisite is number 1. So in this case it's 10 because we want to learn this last move. We want to learn the final move, and the final move requires move 1. So if we can learn move 1, and then we can learn move n minus 1, or move n, and you get 10. So it would be 3 plus 7. What's important to see is, so one way to do this is to think about it kind of like a graph. So let's say you have move 1, and you have move 2, and you have move 3. I don't know, I can move the position of move 3. And then, so move 3 requires move 1, and move 2 requires move 1. And if we want to learn move 3, then we have to learn move 1. And so this is kind of related to something called like topological sort and topology. So prerequisites and that kind of things, it's one part of graph theory, and yeah, so you can kind of think about it in that way. So topological sort. But so you can either use depth first search called DFS, you can use BFS, which is called breadth first search, or there's also another way to do it for this problem, which is that it's guaranteed that a of ij is less than, strictly less than I for each 1 decay of I. So basically what that means is if you're trying to learn move 3, then none of the requirements for move 3 are going to be greater than or equal to 3. So basically, you're always, if you're learning move number n, then it's never going to be that the requirement's not going to be more than the move. So if you're trying to learn the final move, then all of the requirements going to be less than that or something like that. So move number 1 is always going to have no prerequisites, and move number 2 might have 1 as a prerequisite, but it will never have move 3 as a prerequisite. You have that guarantee in this problem. And what that means is that you can move backwards. And so let's say we go from the last move, then the last move requires move 1, and then you can check the second to last move. And if, let's say, the last move doesn't require the second to last move, then we know that the first move doesn't require the second to last move, so we can just skip this completely. This is called kind of a greedy solution. So it's another way of approaching it. So the different implementations, the greedy solution is going to be the easiest, but the first thing is going to be, how do you input this? So first, we get n values, which is the number of moves total, and then we get the t, which is going to be the time it takes to learn. So I have this array learn time, and I have this array need, which is kind of the prerequisites of every move. And so this is going to be a 2D grid. You can also think of this as something called an adjacency list. So in graph theory, there's something called like adjacency list. So maybe look that up. So it's kind of like working with an adjacency list. And then will learn, I just have it whether or not you need to learn something. And then in the beginning, you have we need to learn this last move. So I have will learn of n-1 is true, and the other ones are set to we don't need to learn the other ones. So we get input into we input into t, and then k is going to be the number of prerequisites for that move, and then we add all the prerequisites into the 2D array for this specific one. So I might have, let's say, like 2 prerequisites, then we add both of those into this adjacency list. So that's one way of thinking about it. So the input is something that you just need to get used to, and after a few problems, or if you've seen this form before, then yeah, it'll be easier. But it's this doesn't look like a graph, right? It doesn't look like it much, but once you try some examples, then you can start to think of things in different ways, like kind of like a social network or something as a graph, or scheduling problems can be graphs, or there's something called like flow, where if you have like pipelines or some kind of production or something, and or you need to move cars, or you need to move people around or something. There's all these kind of things, and you can think of it as a connected system, and you move things different places. It can all be graph theory. It's really, really broad, and even though it doesn't seem like it's a graphs, then it actually is graph theory. It's a graph problem. And then the last thing is that you have to fit the answer into the answer might not fit into 32-bit integer. So if you're using C++, you need to use long or long int, and you can work backwards in the greedy solution. So if you don't need to learn the problem the move, then it's guaranteed that none of the other moves are going to require it. And then for every requirement and the prerequisites for that move, you can set that you do need to learn it, and just keep on going. Then you can do this in a greedy way. And then at the end, if you need to learn it, then you can add it to the answer. You can also put this within this loop. So you can go long answer is equal to 0, and then answer plus equals learn time of I. And you can get rid of this. And this is also, so you can fit this within the loop as well. So that's like 2 ways of writing it out. And yeah, for depth first search, this is just a recursive solution. So you're doing the exact same thing, but the big assumption is that if you use depth first search or breadth first search, the pros of using that is going to be that you're not assuming that A of I is less than I. Even without this requirement, you can solve the problem. And so if you have like circular dependencies, like I want to learn move 2, but to learn move 2, I need to learn move 1, and move 1, I need to learn move 2. Then you can kind of learn both at the same time, and you'll solve that problem, right, in real life. So you can actually work with that case, and you can't really work with that case with a greedy solution. But you also don't want, you need to be careful about circular dependencies for infinite loops and stuff like that. So you really need to be careful about that, and check if it's if you need to learn it, then you've checked it already, and then just return. So basically what this does is, so I start at 3, and then I just search, go as deep as I can, and search all the things, and then come back, or something like that. Yeah, look up depth first search and breadth first search. There's a presentation and video on the Danza Competitive Programming Club Discord as well. If you have any issues with that, you can ask any problems, ask any questions, and yeah. And the other solution is going to be a breadth first search solution. So the only difference is that instead of using recursion, you can set up a queue and then add it to a queue, add the node to a queue, and do the exact same thing. So yeah, these are all going to be the same thing. And in the DFS and BFS, I have the will learn this at the very end, but kind of like the greedy solution, you can fit it within the thing. You can fit the adding into the answer into the DFS. You can add it into the BFS. You can do that as well. Have it within the loop. When you set to will learn, you can add it to the answer immediately instead of checking at the end. It doesn't really make a difference. It's also not going to be any faster time complexity wise. Yeah, and that's about it for this week's practice contest. Thanks for watching.